Hello everyone, this is the lecture for section 4.2 for our Math 210 portion of the course, linear approximations and differentials. Okay, so what we're going to do here, okay, is we're going to use, we all know how to take tangent line approximations. We know how to find the tangent line at a specific point to a given function, right? It turns out being able to do that actually helps us out in finding decent approximations to very complicated functions. Okay, and that's what this section deals with. We're going to be using that tangent line and using that tangent line to get us decent, good approximations to more complex functions. Okay, so I think the best way to sort of get this going is to start by giving you guys a good example. Okay, so let's go ahead and take this function right here. F of x is sine x plus 1, right? And I want the tangent line at x equal pi over 3, okay? So you guys should remember this, right? Y is equal to mx plus b. The thing that we're finding, right, is this thing right here. It's the mx plus b, right? So step 1, right, was find m. Step 2 was find b. So let's go ahead and do step 1 first, right? So in order to do that, I need f prime of x, right? And we need f prime of the original, right? So the derivative of sine is cosine. The derivative of 1 is 0. So that's it. Done. I need it at a specific point. So I'm going to go ahead and do pi over 3. So this is cosine of pi over 3. That is 1/2. All right. We're getting somewhere. Okay. Step 2, right? We needed to find b. Okay. So we don't know what b is yet. Okay. In order to do that, right, if you guys remember, we needed an x and a y in order for us to sort of solve that out, right? So that's our first sort of, whoa. Okay, that's going to be sort of our first thing that we need to do. We need to find our x and our y. And to do that, we plug it into the original. So I need f of pi over 3. So that's going to be sine of pi over 3 plus 1. If you guys remember your unit circle, sine of pi over 3, that's root 3 over 2 plus 1. So our point, right, is going to be pi over 3 comma, let me give myself a little bit more space, yeah? Root 3 over 2 plus 1, so my point, pi over 3, that was my x, comma, root 3 over 2 plus 1. Okay? All right. So I need y is equal to 1/2 x plus b through, right, this point right here. And I'm actually not going to rewrite it. I'm just going to point at it. Yeah? Okay. Root 3 over 2 plus 1 is equal to 1/2 pi over 3 plus b. Okay. Root 3 over 2 plus 1 is equal to pi over 6 plus b. B is equal to root 3 over 2 plus 1 minus pi over 6. So if we put all this stuff together, we get this. And I'm going to start using the notation that I'm going to define in a second. L of x is equal to 1/2 x plus my b, root 3 over 2 plus 1 minus pi over 6. Okay, there we are. So now I want to, there's a reason why there's a table here, okay? I'm going to use this to approximate f of x, okay? And I'm going to show you guys this approximation. I'm going to show you guys how this approximation works out. My x values, right, are going to be x values I'm going to choose, but they're going to be x values that circle that one right there, where we got our tangent line approximation. So this one's going to be pi over 3, and I'm going to start going down from here. So pi over 3 minus 0.1, pi over 3 minus 0.2, and then from the other direction, I'm going to go up, right? So pi over 3 plus 0.1, pi over 3 plus 0.2, okay? Okay. I'm going to bring in Desmos now. Okay, so I'm going to plug in two functions. I'm going to plug them in exactly how I defined them, right? There's going to be an f of x. This one's going to be sine of x plus 1. That's my original, okay? And then my next one is going to be L of x is my line that I just found. 1 divided by 2x plus square root of 3 divided by 2 plus 1 minus pi divided by 6. There we go. And look at, lo and behold, right? It is pretty, looks pretty tangent at the point that I need, right? Which is good, which is good. Okay. Now, I want to fill in this table. Okay. And the way that I'm going to do that is I'm going to go into my next sort of line in Desmos, and I'm going to hit that plus table. Okay. I'm going to modify this really quick. That row, that column is going to be x. My next column is going to be f of x, and then the column after that is going to be big L of x. So now what I'm going to do, what's going to happen here, is I am going to be defining, I can define some values, and this thing's going to compute it out for me. Okay, so this middle one, I'm going to make my pi divided by 3. Okay, lo and behold, those values are equal, as they should be, right? They're supposed to be tangent, right? My line's supposed to be tangent at that point, and that point exists for both functions. They're supposed to be equal, right? But now, I want to take a look at this. Pi divided by 3 minus 0.1. Okay. Copy, paste. I'm going to be minus 0.2. I'm going to grab both of these. Copy, paste. Copy, paste. And the difference here is it's going to be plus, plus. Okay. So let me copy down some values onto the left-hand side of the screen here. 1.86602, 1.86602. Those were supposed to be equal, right? But now let's keep going in the negative direction, right? 1.81178, 1.81602, 1.7494, 1.76602, and then let's go into the positive direction, 1.91161, 1.91602, and then the last two, 1.94809, 1.96602. So what I want everybody to see is this. These values right here, they are sine of x plus 1 for these x values. Okay? Okay. These values, right, are from our line, the green one that I have down below, down here, for these x values. Right? Okay. Notice this, right? Between these two, they're supposed to be equal, right? Which is fine, right? And these two, right? They are not far off. They are not exactly the same, right? But if I needed to approximate my function f of x, my sine x plus 1, right? If I needed to approximate those, L of x is not doing a bad job in and of itself. You guys see that? Okay. And then same thing in the other direction, right? The middle column is the actual value at those points for f of x. And L of x is their approximations. And like I said, they're not too far off, right? Of course, if you take a look at the function itself, let me zoom in on the function itself on the left-hand side. Okay, let me get this a little bigger. The function and the line do stray away from each other eventually. I'm not going to say they don't, right? But if you take a look at the values themselves, right, they are not that far off. They are pretty good approximations to your function f of x, right? Okay? Okay, so what I'm going to do now, okay, what comes up next is a quick check. So I'm going to let you guys handle the quick checks for yourselves, right? Do the table, okay? Use Desmos. And now I'm going to go ahead and define the tangent line approximation. So suppose you have a function. Okay, here's f of x, right? And we want at a point A. So this is A. So we know that there is a function f of A, right? There's our function f. You can grab our value A and plug it into f. We get f of A for the y value, right? All right, cool. We can find a tangent line. Bam. This is what we call the L of x. Okay, this L of x has a slope m, which is f prime of A. Basically saying, right, that the slope of this line, L of x, is equivalent to the derivative at that function, at that value A. Okay? That's it. That's all it says. Okay? So, the next line that we have here, right, is essentially saying what we were doing up in that table up above, right? That if we have a function, f of x, okay, it is approximated by that f of A, right, plus f prime of A times x minus A. Okay? It's basically saying that a point, right, can be approximated by the tangent line. Okay? This is us giving it a very special name. That's it. We just call it L of x. Okay? The L of x is what we call the tangent line approximation or the linearization of f of x. It's essentially the tangent line at a specific point x equal a. That is it. Okay? That's it. Okay, moving on, I need to cover differentials. Now, differentials does fit into this. It doesn't look like it does, okay? But it does, okay? I've been using this notation, right? Whenever we say dy over dx, we mean it to say it's the derivative of f of x, right? But I sort of pulled it out of a hat. I pulled it, up from my sleeve, right? Way back at the very beginning of the semester. And I never showed you guys why that is, right? We never defined what dy and dx really meant. Okay? So that's something that we're going to cover right now. Why? Why do we have these things? Okay? So first of all, let me define dx. Dx is an independent variable that can be assigned any non-zero real number. Okay? Once we define dx, we can define the next thing, dy, as this, okay? And notice how the f prime is there, okay? And just remember, right, f prime is the slope of the tangent line, okay? These are the textbook definitions of what dx and dy stand for, okay? Now, what do they mean in practice, right? Essentially, dy and dx are infinitesimally small distances on the x and the y axis. Okay, so that means dx is going to be the infinitesimally small distance on the x-axis, and dy is an infinitesimally small distance on the y-axis. Okay, that is defined by the dx. That is defined by that infinitesimally small distance on the x-axis. Okay. If you remember from high school, right, when you tried to write down a slope, they had you looking at this thing on the right. They said delta y divided by delta x, that's your slope, right? Eventually, right, that dy dx, I turned into derivative, right, the slope of the tangent line. This is the reason why. Okay? Okay. Now, just from this definition, right, we've got a fair amount of pretty important information that we can pick out of here, okay? So suppose, right, we have a function. Let me actually draw a nice function. Let me do whoosh, there we go. Okay, this is my f of x. Here's my point A, okay? And I have my other value, f of A, along the y-axis, right? Okay, we know now, right, that at this point I can do a tangent line approximation. I'm going to try to draw a line. There we go. This right here is not f, this is L of x, right? And now keep in mind, right, that my slope is f prime of A. Okay? We know these two things, right? That f of x can be approximated, right, by f of a plus the derivative times x minus a. We gave that a nice name. We gave that L of x, stating that that is the linearization or the tangent line approximation to f of x. Okay. Now I'm going to do something special. Okay. I'm going to grab my x value and call it something specific. I'm going to call it a plus dx. Okay. What that means is this. I'm going to call this other value way over here a plus dx. Okay. Which means this distance right here has got to be dx. Okay. I am going to be looking at two values here. I'm going to climb these up vertically, straight vertically, try to. One point's right there, and the other point's right there. Okay? There are two values here. I'm going to grab this one, and I'm going to go straight across. Notice that this value right here, is on f of x. So then that means this is going to be f of a plus dx. Okay? There's another value. If I grab this one and go straight across, this is L of a plus dx. Okay? Okay. We're moving along. So let me scroll down really quick. If I do that math right there, right? If I do this and I plug them into here, I get the next couple sets of equations, okay? That my f of a plus dx is approximated by this thing, okay? using my line, I can say this is true, right? Both of these imply the next part over. Okay? Now, these things at the end here have a special name. F prime of x dx, right, or f prime of a dx is equivalent to dy. We get these two equations, right? That f of a plus dx is equivalent to f of a plus some small infinitesimal distance dy, right? So we call that thing a name, right? We say that the linearization, the tangent line approximation of a plus dx is the same thing as my f of a plus an infinitesimal distance dy, which is f prime of a times dx. What this essentially is saying, right, is we can approximate, right, if we have a value x equal a, and we move off of it just a little bit, a very small little tiny bit dx, right? It's the same thing as f of a plus or minus a small little distance dy, okay? Moreover, okay, we can use this definition to provide an amount error in our dy, okay, given a specific dx, okay? So this not only does this give us an approximation, it can tell us how far off we are, okay, at most. Okay, now where is this dy in our picture? Our dy is going to be this little piece right here. It's going to be that little distance right there. The distance between f of a plus dx and L of a plus dx. Yeah? Awesome. Okay. So what does that mean? Let's go ahead and do our original example. Okay. I'm going to write this down here just so we keep track of it. Is equal to 1/2 x plus root 3 over 2 plus 1 minus pi over 6, right? Okay. I can provide an approximation, right, to this value right here for this function right here. And I can use my linear approximation equation, my L of x, to do so. So instead of using sine of x plus 1, my original f of x, I can just go ahead and do L of pi over 3 plus 0.1. And if you do that, right, 1/2 pi over 3, whoops, plus 0.1 plus root 3 over 2 plus 1 minus pi over 6. And if you do this all outright, 0.1 plus root 3 over 2 plus 1. If you take a look, right, this right here is f of a, right? My 0.1 is my d, oh, sorry, not 0.1. Got ahead of myself, 0.05. Okay? And if you compute this out right here, you get 1.9160. Okay, so two things, right? that 1.9160 is a good approximation to my function itself. And I used my line, I used my tangent line to do so, right? Number one, that's something we got, right? My dy, right, is 0.05. That's how far off my approximation is. So that means, right, this value, 1.9160, is a good approximation. The farthest off it can be is 0.05. Okay, pretty useful stuff, huh? Okay, so I've got a couple quick checks for you guys to try out. Okay, now, uh, in theory, right, everything that I just said, if you watched it enough times, right, will make sense. But probably a question has come up for everybody here. Why? Well, what's the point of all this, right? Okay. Turns out something like this is very useful in manufacturing. Okay. If you know for a fact that you can manufacture something with a specific tolerance, right? With a specific measurement that you know you're going to be off of at the most, right? Can you tell me how far off another measurement can be of the same thing? Okay. So, as an example of what I just said, right? Suppose you are manufacturing ball bearings. Okay. And the radius of these ball bearings are 0.7 inches. Okay. If your measurements are correct, if you can manufacture them to within 0.001 inches, right? How far off is the volume of said ball bearing going to be? Okay. So here's my ball bearing. Let me make it a little smaller and give myself a little bit more room. Here's my ball bearing, right? So here's, pretend it's a sphere, right? We know that this thing has got a radius, right? And we know this radius is 0.7 inches, right? Okay. We know the volume of a ball bearing. We know volume of a sphere, right? That is going to be V of R is equal to 4/3 pi R cubed. Okay. All right. So now there are two things that I want to define. Okay. There's this dV and this dr. Okay. dV, right, is the infinitesimally small measurement in the volume. Okay. The R is that. It's the infinitesimally small measurement in the radius. Okay. Okay. So now the question is asking us here, how far off will our volume be, right? Okay. This is where we're going to use this notation. So what I'm going to do is this. I'm going to do dV over dr. So what, if you guys remember, right? This is telling me to take the derivative of the volume with respect to my radius. So I'm going to take the volume of the equation above it with respect to my radius. That's going to be 4/3 pi. The derivative of r cubed is 3r squared. The rest of the stuff, right? 4/3 and pi, those were constants. Those just got to come along for the ride. We get left with this. I'm going to multiply through by dr. That'll cancel that. I get left with dV 4/3 pi 3r squared times dr. Okay? So now look at what we have. Okay? If I have a tolerance, if I have an error amount in my radius, this equation can give me my error amount in my volume. Got it? So now what's left, I need my dV. This is the thing that I'm finding, this right here, my dV, right? So this is the question. But I know what my R is, and I know what my dr is, okay? My R, right, is going to be the 0.7 inches, right? My dr, right, that is going to be the 0.001 inches that I think, right, is where I'm off. So I'm going to take all that over here. dV, and it's supposed to be a big V. 4/3 pi 3.7 squared times 0.001. Okay, 4 pi 0.7 squared times 0.001. Let me grab my calculator really quick. 4 pi, where's pi? 4 times pi times 0.7 times 0.7 times 0.001 0.00666157. Okay, so what this is saying is this, right? If well, let me start using units for real. 0.001 inches will be off by 0.006157 inches cubed. So notice what we did here, right? If we're able to determine how far off one measurement is, right, we can provide an error for the other measurement, all based off of the calculus. Okay, like I said, this is useful, very useful when it comes down to manufacturing things, if you're making anything, right, or if you're looking at tolerances for things that have been created. Sometimes overall quality assurance uses this stuff. Okay. All right. What comes next, I believe, is some quick checks, really quick ones. Okay. And then after that, lecture questions. If you've got any questions on the stuff that I just covered, ask me during our quick check time. Come downstairs to my office hours, come visit me on a Friday, or find me in the tutoring center, usually there. Okay. All right. Besides that, happy studying.